So yeah, thank you very much for attending. I think, yeah, this was a little tough, like, because I had something in mind, and then obviously the last 2 weeks, even beyond the political situation of what's going on in the US, like we have DeepSeek, so I kind of try to weave things in. So I think I have a tendency to try to like kind of push, maybe add maybe a little bit too much. So we'll see what I can get done in an hour. But just to start, I wanted to get a little bit of a sense of like people's backgrounds. I don't know how many people are, would maybe classify themselves as novices or users of some of your large language model technologies. Show of hands, just rough. How many people feel like they're experts or not, maybe not, so like mid-level, okay. And then experts, okay. So kind of a mixed crowd. So I think what I wanted to try to do is really, in some ways, kind of like, kind of paint a narrative around like how the LLM space has evolved in the last 2.5 years. And I think a lot of that actually kind of really can reinforce some of the types of things that large language models are really good at and what they're not good at. And I think it also kind of follows like some of the more macro trends. And hopefully, at the end of this, I will get to DeepSeek and like what it means or doesn't mean. But I think it really kind of paints, I think, a very coherent, consistent picture around like how a lot of these technologies are evolving. And, I kind of wanted to kind of just spend this time kind of talking through that. And again, I will try to keep it into like the 50 minutes to an hour, and try to leave as much time as people are open to or are interested in from a Q&A standpoint. So, all right. With that, just quickly, so like Composed Labs, we do application development, data engineering, and artificial intelligence. I think the main reason, we have been doing a lot of like AI projects, especially over the last 2 years, as with a lot of other companies. And, I think a lot of our learnings I try to incorporate into this in terms of like how we're thinking about it, how we try to use chatbots, how we try to use RAG, how we try to use agents, and, kind of want to share that. Justin actually mentioned last time, and kind of a little bit to the comment around like some of the technologies. I don't know if people have like worked in the marketing space or advertising, like there's this notion of like a MarTech stack. And I've always really liked this visual representation. And these are just some of the examples of the tools that we're using today. Now, obviously there's a broader list of that, but I think Next.js, like Vercel, AI SDK, if you are interested in building kind of friends with a lot of the streaming AI capabilities, which is typically one of the more challenging parts. Vercel's got a really great framework. We've done stuff in, Gradio, Streamlit, a bunch of other stuff. A lot of people, our clients, are looking at like, say, your various messaging solutions, but, choose one. I'd probably like, recommend people take a look at Next.js and Vercel. Yeah, go ahead.
I'm seeing a lot of people with their phones.
Yeah, I will. Yeah, hit me somehow. I'm more than happy to share this. So feel free to take pictures, but also I'm happy to give a higher quality PDF version of this. So, I think in the middle, I'm probably a little bit too biased towards LangChain. I know they've had some ups and downs from a market standpoint, from stability, but generally from a LangGraph, from a Langsmith, a lot of the capabilities that they bring gives us a lot of flexibility and robustness. And, I think that's a set of technologies that we use quite a bit. LLMs, I think we're a little bit more, like kind of a little bit more wide. OpenAI is probably what we use the most, just primarily because we understand how it behaves. Now, it might not necessarily be the best in every specific use case, but I think like the predictability, the stability, the understanding of how it works is really critical. I'm a big fan of Together.ai. If you're really interested in the open source like inference, they've got really great things. There's a bunch of vector databases, open source, as well as like kind of some really strong ones like Pinecone that are, SaaS. There's a bunch of tools out there. Observability, as I mentioned, I think Langsmith, weights and biases are probably the two ones. And then, from an infrastructure standpoint. So really, we generally have shied away, honestly, from a lot of like the native tooling from a lot of the big cloud players. Obviously, they're adding a lot of stuff, but it somewhat locks you into their ecosystem. And I think we've been at least trying to look at more kind of a best of breed. So I figured I'd kind of share this at the beginning because it was kind of a question that Justin had. And just these are things that we're using. Now, obviously, there's a bunch of other things that we've used, but this is kind of our reference stack or our LAMP stack for way back in the day, if you're kind of looking at that. Yeah.
Can you explain why Perplexity is in the tools section?
So a lot of cases, like we're using APIs for like kind of search extensions. So obviously they have other capabilities, but generally what we do are typically building more kind of robust like solutions. So we're using them as a data source or a feed. So obviously they have their own stack. You can use it in many different ways. So good question. We're probably using Tavily more. Like if you're purely looking for like web search type stuff, it's a little bit easier to work with. I mean, unstructured's got some really great stuff. I guess I don't have like Firecrawl's another one that we use quite heavily for like kind of web scraping type stuff. Any other questions or comments? All right, I'm gonna go for like 50 minutes now. So, all right. So I never seen. So I don't know. Like people probably know Gary Marcus. So he's one of the a very well-known AI researcher, as well as he posts quite a bit. I would say he's probably a realist in many ways. I think there's a lot of battles between like the optimists in the AI world, and I had never seen this quote before until yesterday, and I think it felt like it really summed up what I wanted to try to get across. And really, I love this like in the middle, like these LLMs, like they obviously are massive correlation engines. I'll kind of give a little bit of an explanation of what that means, but like this hilariously fail, breathtakingly win. Like that to me is really how these things work. Like it's unbelievable, like what they can do, but also like there's just like basic stuff that they really struggle with. And I think what I wanted to at least try to tease out is really, I mean, somewhat of that last question there, like, what are the questions, do these things like actually do well or not? And I think part of it is, I think a lot of it does come back to transformers. Like, so some of these buzzwords, not necessarily buzzwords, but some of ththese concepts, I at least want to help try to provide an appreciation, maybe some intuition in terms of what these things do. So like when you hear, attention mechanism, or if you hear transformer, you at least associate like what that is, as well as like, why does it actually matter within your world? So people saw my last talk, like this is really how I've kind of somewhat structured this presentation as well. Somewhat, as I mentioned, like from a timing standpoint, how we've really evolved. So, end of November 2022, to some degree was really like kind of just like, ground zero for, this large language model movement. Now, obviously there was, E3, there was like, ones before that, but ChatGPT really kind of exploded on the scene, and it was very much chat-based, and I think it really captured people's imaginations. Now, if you're familiar with Gartner, they called, Gartner peak hype cycle like August of 2023. Generally, it is very much more pervasive in everything we do. I would say it's like kind of beyond like the hype curve, but obviously, people are continuing to use it in a variety of different ways. The last few years, I think we're very, very data-centric. So I think once people got familiar and comfortable with, all right, I could actually use these chat models to kind of interact, now I wanted to use it with my own data. And I think that was a really like Retrieval-Augmented Generation, RAG, which I'm guessing most people in this audience have heard about, was really kind of this next wave. From my perspective, I mean, roughly like mid 2023, it kind of like popped on the scene. And then, I think it's kind of maybe it's past its peak, right? So I think RAG is a relatively established concept in a relatively pretty short period of time, in the way of like, how do you go add data, some context to your large language model to kind of accomplish different things? And there's obviously a lot more nuance there, but that's that kind of wave. And then the third wave is really around agentic. So, I think from my sense, I think early 2024, there were some concepts prior to that. This diagram was actually from like, I think March or April of 2023. So it's not like some new concept. But I think people really started digging into like what some of these agentic frameworks could help do for us at the beginning of last year. And I think especially over the last quarter, things have really accelerated, and I want to kind of spend some time there. So all to say is, from a content standpoint, I really want to kind of, number one, kind of at least talk about some of the grounding principles of what these large language models are. So transformers, attention mechanism, hallucinations, that type of thing. Kind of want to secondarily, the second piece, really want to kind of talk about some of the kind of the data principles of how large language models operate. And then the third one, really getting into a little bit more like where we're at today. So how do we think about these reasoning models that have just popped out of nowhere over the last few months? How do we think about these agentic frameworks that are giving us, ideally that next level, that next step function in terms of what large language models can do? So, and I think what hopefully, I give is an appreciation that like a large language model, they're all very distinct. Like there's very specific reasons that they're being tuned. And I was trying to think of some analogy. I thought about like chef's knives. Like it's really, you could give a good chef like whatever knife and they're going to get it done. But I think a lot of these large language models are being optimized for very specific purposes. And as we're model builders or we're system builders, we really want to understand how that fits within that broader kind of landscape. And I think secondarily, and I guess I was, maybe continuing the kitchen analogy, really when thinking about like an onion. So I really, hopefully as part of this talk, you know, maybe not necessarily like every one of the concepts will kind of resonate, but ideally you have a better appreciation of like how potentially all these things kind of fit together, or how are the different layers structured. So as kind of mentioned, you know, pretty quickly, transformers, hallucinations, and alignment. I think those are like kind of three core concepts that I think are pretty important. I'll kind of talk about each one of them in a little bit of a different section just because of those topics. The next one, I kind of like bundled together. A lot of this is around that data side. So how do we start think, or how do these large language models really use data, and some of the nuances, some of the you know, the quirks about it. So we need to be aware of that. And then kind of ending up with like reasoning and agentic AI. So these are kind of the three kind of sections that I want to kind of talk about. So kind of jumping into transformers and attention. You know, and again, like this is kind of a repeat of if people attended the kind of the speed talks, but really, you know, I think a lot of the innovation, a lot of the explosion, you know, over the last, you know, 2 to 3 years was really driven by like kind of a very clear intersection of like kind of three major factors. So like, you know, there's really a lot of focus on like building larger models, more complex models. There's really a huge focus on kind of like leveraging more data to train these models, and then a huge amount of compute. And really this like kind of intersection really just hit at a very common point with ChatGPT, and really like all the right ingredients, all the pieces were there. Now, you know, I'll talk a little bit like, so transformers, reinforcement learning, human feedback, I think was really important. And then even as we get into these reasoning models, like, you know, something called chain of thought is becoming more relevant, but really like these three kind of dynamics are really what kind of drove us to kind of where we're at. And I want to kind of dig into each one of these a little bit more. So just quickly, I honestly am not sure if it really matters that much. I think in a lot of cases you can just think about like a large language model as like a black box, but you know, like they are fundamentally neural networks. And I think if you are thinking about kind of like fine tuning or training it, at least having some appreciation, you know, there's some input nodes, there's some hidden node layer, and then there's some output nodes. And then the reality is a lot of these large models, like these, you know, state-of-the-art models that we're talking about have, you know, when you hear about like, hey, this model has, you know, 400 billion, you know, parameters, it's really like the yellow nodes typically. So, and then, so that's kind of one dimension. And then secondarily is really the connectivity. So those lines between it. So all to say is, I think it maybe is helpful, like to kind of, at least from a biological analogy, like a lot of these models are operating like your neurons in your brain, right? So these are, you know, going back to the perceptrons, like the 1940s, 1950s, like early AI, and these things have just expanded, you know, significantly for where we're at. So this is kind of like this fundamental framework that was just kind of going along. You know, I think people were really kind of pushing the envelope, trying to figure out like, how do we leverage these in a more robust manner? And in 2017, some of you might have heard, like, so attention is all you need. So Google, the team, the DeepMind team within Google released this paper, attention is all you need. And it really caused this huge explosion. So it kind of took the fundamental kind of like neural network architecture and added this notion of a transformer and attention. And it really allowed, you know, it really motivated this like explosion in the different approaches to kind of building these large neural networks. And part of it was like algorithmic. So really kind of focusing either, I mean, I won't go too much on like, so an encoder part, decoder part, you can kind of have them together, but also like just really what leverage the data, what's the data you leverage, how large the parameters are, but it really kind of caused this explosion. And so specifically this attention mechanism was really kind of novel, and that was really trying to look at like in a broader context, like how you know, the context in your natural language. So before this, a lot of the models were like kind of more feed-forward neural networks, if that's something you've heard about, where you're just kind of looking backwards in time and trying to do your best job predicting. Whereas a lot of these large language models, this transformer, this attention mechanism, really wanted to think about, all right, how do I go figure out the correlation of other words, both before and after, to try to like figure out a better context. Now, I think this right-hand diagram, you know, in my mind really helps. Like, so there's like kind of the word interest is there twice. Given the context of the words before and after, you know, they're, you know, it's the same word. However, it has very different meanings. And a lot of your previous to transformer large language models or your neural networks were not really necessarily able to pick up that distinction. And I think that was a very important kind of novel thing, because like language really, you know, there's a context. So just knowing a word doesn't really necessarily help if you don't have like that broader context. So like the attention mechanism, I think, was a very much of a game changer. So adding on to data, adding on to larger models, adding into kind of more, more complex, ways of training your models, this attention mechanism was really important. So what you can think about it is it's kind of like a distribution. So, like this is an example from some like legal documents that, what is like what's the first word? And you can imagine, like if it's a negative score, it's a very unlikely scenario that word is going to come first or within that context. And then you have this mix that are kind of a little bit higher. So this attention mechanism in like softmax specifically is giving you this ability to kind of like give you a probabilistic distribution of like what your next word is. And what this kind of leads to is there's at least, if people have heard of like model temperature, it's kind of this dial that you have within a lot of your large language models that basically kind of going back to this diagram, like, and it's like, so if I have like, say, a temperature of like 0, I really just want to choose what is the most likely word. And I have a very, very tight distribution in terms of what next. If I have a very high temperature, I'm gonna have a lot more variability. And this kind of example like was kind of really nice kind of visual representation for me. So like you see the word I like red blank, most likely, I think just given at least the training data, most likely apples. So if I have a very, very low temperature, I'm going to choose like the most likely word. But as you see like your temperature increase, you're going to get a lot more variability in your response. And the reason why I think this is important is, and it just maybe as a caveat, a lot of like your ChatGPTs, a lot of your base models, they're typically in temperatures in like the 0.7, like 70%, 80%. They're really not typically here. Now, if you're doing something in like, like healthcare, finance, you're tuning your model down. But I think what they were trying to do is really kind of, this like creative to deterministic kind of spectrum. So like for a lot of people, using ChatGPT, you're typically using it, hey, I want some variety. I want some variation in my responses. And in many ways, that made it sound more human to people. Whereas if it's, if it's a little bit 0, you're just getting a robotic answer, right? Like it just sounds like, hey, what's the most likely next word? And you just didn't have as much like kind of character. Whereas, they've tuned it, like I think most of the models are in this range, and they're finding, hey, that variability, you're going to have a little bit of randomness in the way that your LLM responds. And actually, as people, that actually is something that we like, as opposed to it being, very mechanistic. So let's see, I think this model temperature is like a very important thing to kind of keep in mind. And it's somewhat of a result of like kind of your attention mechanism. So as you're training these large language models, they're really trying to figure out, all right, what's the next word? And this is at least one of the dials that we have as users of these models to be able to say, hey, do I want to turn up the dial from a creativity standpoint, or if I want to turn it back? So now another example kind of in that, leveraging your attention, like, so now you have hopefully some kind of concept of like what attention is. There's also chances of biases. And this is, I think, a really good example where depending upon the underlying data source that you use to train your model, again, like sometimes it might make a difference, sometimes it might not. But this is a good example where, the doctor asked the nurse a question, and then she said, he said. It kind of shows the correlation of like what's the most likely. And again, given the training set in general, nurses map to the she, he mapped to the doctor. Now that might be an accurate interpretation or not. However, this is kind of like a potentially subtle bias that these large language models have based upon what is the most likely behavior within their training set. So this is, again, kind of another concept that we want to just kind of keep in mind as we're kind of thinking about these large language models. So this might be a little bit of a diversion, but I just like this one's kind of a quick one. But I think another thing that people are really focusing on right now is like, these like smaller large language models. You have LLMs and now SLMs. But I think what it's really like predicated on is people really focused on how do I make bigger models? And as I make bigger models, and I really like this visual representation, it improves or increases the amount of capabilities that you have. So obviously, if you're looking at a GPT-4o or some of the larger models, pretty significant number of parameters because they're really trying to be a generalized model. But if you're really looking at kind of more of an optimized, if there's a very point reason, you might be able to get away with a much smaller model. And I think what's interesting, so this is a chart from Microsoft. Microsoft has been very, very aggressive about trying to build smaller models. So on the x-axis is a number of billion of parameters. These are generally pretty small models. And then this one, MMLU, is just one of the more like standard benchmarks that are out there. But you basically kind of see, so like Gemma, Llama 3, Mixtral, like there's kind of a curve. And what they've been able to do is either like, say, if I've held, say like 8 billion parameters, this is what my model is capable of. They kind of basically like move the curve up. So given I can either say like, shrink the model to kind of get the same level of capabilities, or I can, keep the parameter size the same and get better extra capabilities. So all to say is, I think a lot of this trend is being driven by, like Apple Intelligence, Google. We're beginning to think about like, how do we have these like kind of more micro agents, micro LLMs, or small language models like running on our device, and that's kind of a trend that's kind of going on. So kind of wrapping this, like these section, just like from a transformer standpoint, and I think a lot of this is coming back to, where are we getting these benefits? And this chart is kind of mapping out, over time. So I think, 2014 was kind of like, a benchmark of 1. You can see like kind of the increase in the effective compute, the capabilities of these models over the last, from the last 10, 11 years. And we basically have had like a trillion, 12x orders of magnitude improvement. And what I think, I like this chart because it kind of shows how critical, and obviously, before DeepSeek got released, it kind of explains why, NVIDIA's stock price has been going like crazy. But also I think it's really important to show that there's been pretty significant algorithmic improvements. So I think the transformer model is very important. You kind of somewhat see an inflection point here when I think like kind of the attention paper was released by Google. But all to say, we're going to continue to have like algorithmic improvements. We're going to continue to have like compute improvements, and that's really driving us to kind of where we're at. So the next section I want to talk about hallucinations, and hopefully it's kind of like at least kind of, now you have like at least a concept of like what the temperature mechanism. So it's really trying to predict what the next word is. You could very naturally think, okay, this is potentially a very good reason why the things hallucinate. So wanted to start with like, what are different types of like hallucination? So the first one is like, input conflicting. So like you basically, you provide some input and just generate some noise. Now, obviously, if you're trying to predict the next word, that kind of can make sense. Context conflicting. So, like potentially even they can like disagree with content that's been created in your history. So I think we've been seeing a lot of interesting scenarios as we have these longer running processes. As you're building up history, it gets a lot more complex for the LLM to kind of stay consistent. So this is kind of a really interesting nuanced case. And then there's also like fact conflicting. I think this gets a little bit more challenging. So I think most of your models say, hey, we got trained up until, like September 2024 or whatever. Like this is kind of a little bit of a moving target. But obviously that is potentially like, so a lot of people are beginning to use ChatGPT more like a search engine, and they're looking for the latest news, whereas there's really kind of a news limit. Now that's obviously a reason why OpenAI is adding in operator, other ways of kind of incorporating additional information. But these are at least potential ways from a hallucination standpoint. Now, I wanted to kind of show this to both map like kind of how models are trained, as well as I think the next slide will really talk about where, those types of hallucinations, like where could they potentially be inserted. And I think there's kind of like 3 really big buckets in terms of how large language models are both made and used that I think are important to keep in mind. And I'll kind of keep referring back to this diagram because I think it's a very important one. The first is really, this pre-training. So I'm trying to create a base model. So you basically throw a bunch of data at it and you build a model. And that's really kind of the base model. That's like kind of step 1. The second phase is really this kind of the domain specific fine tuning. So how do I take this base model and I kind of shape it to how I want it to behave? And then there's a third one, which is really around, all right, how do I, once I have this like kind of fine-tuned model, how do I go use it? And there's a lot of parameters I have there. So these are these kind of 3 macro things that I think are very important to kind of keep in mind. And, from a hallucination standpoint, really mapping to this. So from a training, one of the reasons why I might have, like pre-training, there might be an architectural flaw in the model, suboptimal training objectives. There's a number of kind of things that model builders need to be watching out for. Generally, as users of these, we don't necessarily need to worry about that. I think the data biases are a lot easier. So maybe, there's a lot of notions of like, how do I go, inject like incorrect information in some of these large models? That's, flawed data source type of things. They might forget how to like kind of recall things. And then from an inference standpoint, there's like, defective coding strategies. This is like a sampling. There's a randomness going on. So there's kind of like layers of different ways that kind of like your hallucinations can potentially input, enter into your system. And I think some of it is like, thinking from a training standpoint. That's why we typically rely on, the state-of-the-art kind of model builders, because like generally they're doing a much, pretty good job there. We want to understand what data is being used from a training source standpoint, so we can understand some of those. Obviously, DeepSeek is a little bit biased towards providing positive information about China. You kind of need to know that. And then from an inference standpoint, there's like, as you're using these things, if your temperature is turned up to like 10, you're going to get a lot more hallucinations. So this might be a little bit hard to see, but yeah, I pulled some new data yesterday. So I kind of wanted to compare over time. So there's a number of these kind of like benchmarks that compare what's the percentage of hallucination. And I think this is very important for you to keep in mind. So if you're building something and like, if it's in medical and you have like a 3 to 5%, hallucination rate, that's a problem. Like you really want to try to drive that down. If you're trying to do something creative, it's maybe not necessarily as big of a deal. But I somewhat wanted to see just like how, in general, a lot of the large language models are trying to reduce the hallucination. So the way that they ran this test is they basically have like a list of like 1,000 documents. They ask a large language model to summarize each one of them, and they're basically determining how effective they are in summarizing that. So if it's like making up data, it's going to have, it's going to fail that, and it'll get a different percent. I was blown away. So I pulled this middle column. You might or might not see it. So the top models was 1.3%. That was like around the time, like 2 weeks ago. I just pulled it like yesterday, and we've already had like the top 4 or 5 models. The top 5 models, 4 models are like completely different. So these things got released in the last 2 weeks, and we've had a reduction. So like summer of last year, we were around 3%. So the state-of-the-art models were around 3% hallucination rate. We're around 1.3% like 2 weeks ago. Now we're like 0.7. So it's, and again, I think this is a very positive thing, because I think a lot of the model builders are recognizing, hey, this hallucination is a very critical problem. We need to solve that. But also it makes it really, really hard. If you're going to build a solution, most of your intervals are not, most of your dev intervals are not like 2-week intervals to release something. So
you got this from Hugging Face, or did you get it?
Yeah. So like, just separate. Yeah, sorry. So like all of my, I really try hard to source. So so on the bottom, so there's a really nice hallucination leaderboard that they have out there. So there's some, again, I guess I wasn't meaning to check it. I just wanted to check, and I'm like, whoa, these numbers really moved like in the last like 2 weeks. So, but again, you can look at it. So Google Gemini, it's a lot of your reasoning models. Those are the ones that kind of like are now, top of the pyramid, at least from that perspective. That again, that's just one factor, but it's moving pretty quickly. So I'll just spend a little bit of time on this. I mean, I showed this one last time, but again, I think part of it is talking about like sometimes hallucination, if you're trying to be creative, it's really valuable. If you're doing something, a medical procedure, not so good. However, it's really interesting. A lot of the science literature, especially around protein folding. So I mean, there was a Nobel Prize given for some of the work that partially driven by some of the work that the Google team has done. But really, it's really interesting. I mean, you read, like they actually have like an abbreviation, learning from hallucination. So it's an LFH, right? So this specific scientific community, they actually really like the fact that like you're trying to like, it's a combinatorial problem, right? So they're trying to figure out, how do I train these LLMs with the rules of how my proteins behave? And I just wanted to run crazy. And it actually has been really amazing at kind of basically, defining like new ways of, creating new protein foldings. But I mean, this is kind of just a selection of stuff there, but it's been really interesting how, we view hallucinations probably necessarily as a negative thing, but depending on like how you're trying to use it, if you're really trying to like explore, like, and be creative, it can be very, very powerful, even within the scientific domain. So, I felt very bad. Like this was my punchline from my quick talk. I didn't get to it, but I got pulled too quickly. But I just love like nobody knows. Like all to say is, I think maybe somewhat summarizing this, I think generally hallucinations, is it a feature or not? Like nobody knows, right? It is fundamentally part of how these large language models behave. And then like we just need to keep that in mind as we're kind of like building models or using these things. So this is a little bit of a bonus topic. I think alignment is, I think, a very important topic as we kind of get a little bit more into the reasoning side. But going back to that, that diagram I had, so there's like a pre-training, you create a base model, there's kind of this fine-tuning. It's really, there's kind of 2 elements. There's a base, you build a base model, throw a bunch of data at a neural network, kind of tune a bunch of the weights, you get something out, and alignment. And I think the reason why I wanted to highlight alignment is I think it was very, very critical in motivating why ChatGPT exploded. And I think OpenAI, I mean, they have for sure been one of the biggest proponents in terms of driving larger models. You know, they've thrown more hardware at it. They think they've been really, really innovative in a lot of their algorithms. They also bet very, very heavily on reinforcement learning, human feedback. So I think a lot of their, their initial models, they very much leverage, people basically judging the output. And what this alignment process, what this step in the model training process allow these models to behave or respond a lot more like what we would expect a human to respond to it. And that's, I think, really one of the reasons why, if you look at the Turing test or however you want to do that, even like ChatGPT 3.5, it responded very similar to how a human would, because they tuned it extremely, they really spent a lot of time on the reinforcement learning human feedback. And I think that's an important thing to keep in mind, because they really, one of their objectives was really, how do I make this behave like a human? And that will, I think, become interesting. Like if you're thinking about how do I go train my model to reason, I don't necessarily never really care as much about it acting like human. I want it to go be a good reasoning machine. Yeah, go ahead.
Well, I would tell me what.
Yeah, no worries.
So if you are interested in RLFH,
Yeah.
will you think a human, if you have done too much of alignment, you're biasing the model away from being effective for RLFH.
Well, it's hard. Like if you're doing too much, you're probably just, you're constraining it too much to how you want
That's
to
right.
So I think there's this, I mean, you normally, there's a curve that you have, like, all right, how do I, well, it depends on what you want. Like if you want a very specialized model, I want to train it very specifically for that scenario. I think the reality is most of these large language models kind of get into the number of parameters. I'm trying to build a larger generalized model. So I'm trying to solve a much wider set of problems. So I'm,
So if you're trying to discover something you're almost saying that I don't want people to tell me, because that will narrow it down. They will only give me answers which they've already thought of. I want to really see what normally experts would not have thought of.
Correct. That's why I think, I mean, at least, I don't know. I mean, the temperature dial might be a little bit too bit of it, but that is like, I want it to be more variable.
Okay.
Right. So you're really trying to explore different spaces. Now, in the case of specifically like protein folding, the LLM is not doing natural language. It's saying, all right, what are the rules of like how proteins behave, right? So there's more of a chemical biological process there. Whereas in our world, like we're typically thinking about natural language. But now when you think about closed domains like math, like science, in general, you're not necessarily wanting human, reinforcement learning, human feedback. So this is skipping into like the deep seek and like kind of the motivation for that. But honestly, I just wanted to quickly show this diagram, because I think this was, this really like kind of was like eye-opening for me. So this is for Llama 2, Meta released basically like kind of the X and Y axis. X axis is helpfulness. And, like they have two different ways of judging it. Percentage wise, you can determine like what helpfulness means and harmlessness. And I think what was to me like most insightful is like how drastically that alignment process actually improves or changes the way the model behaves. And I think why this kind of stuck out to me was that you really need to understand whoever's building the model is trying to align for specific goals. So like if you're looking at a Google, if you're looking at a Meta, if you're looking at a DeepSeek, if you're looking at an OpenAI, they're leveraging this real time, this reinforcement learning human feedback specifically tune the model for their scenario, the way that they're defining harmlessness as well as helpfulness. So all to say is like your base model, was pretty not very good. I mean, it wasn't not necessarily well, it didn't score very high. Whereas as they went through these additional like kind of tuning cycles, they kind of tuned it for very specific types of behaviors that they were looking for. So all this is, I think this alignment, that second step in your training process is really, really critical for the way that the model behaves. And I think that's also a good, it's a segue into kind of like when we get to like the reasoning capabilities of some of these models. So
is there some kind of benchmark for people to understand helpfulness versus harmfulness by each LLM?
Well, I mean, so in this case, it's interesting. So like Meta, they compared it. They wanted to use ChatGPT, so they wanted to use an LLM as a judge versus Meta, this was a model that they had. So it's kind of a fuzzy space. Like there's probably different scoring criteria, but like you can see kind of generally you're having that same trajectory across both your harmlessness and your helpfulness dimensions as you're kind of aligning your models.
What I meant is, if I want to really understand their philosophy, is there a way for us to
No.
understand?
That's why, but that's why, like, you know, in some cases it's becoming political now. So it's like, okay,
Okay.
Chinese models versus US models versus Europe. Like, you know, Mistral does their own thing, right? So this is pretty nuanced. And this is why at least we have stuck with models that are just generally more used, because then we have a better understanding of like potentially how it's going to behave in certain scenarios. Whereas like DeepSeek right now, you know, it's like nascent, right? So people are still trying to figure out what are the boundaries
Sure.
where it behaves. Like obviously it's not going to say much about, you know, like nothing against the communist government. However, like what are other things that might or might not be in that training set? So okay. So kind of jumping. So this is kind of getting into the second section. I won't really spend a ton of time on RAG, but you know, context lengths. I think people are probably familiar with that. So that's the number of tokens. So tokens is roughly kind of like, you know, like a 75% of a word. So it's kind of a, you know, it's kind of a weird mapping that you get used to when you're thinking about large language models. But this thing is just exploded. It's kind of capped out. You know, there hasn't really been a ton of noise since like a lot of the Google really pushed the envelope, getting to million, 2 million. But generally, most of these models, you know, like in 2023, you know, we were talking about 3,500. Now, generally, like 100 to 128,000 in that middle range is really where most of these models are at. So really, I think this was important at the beginning. We were very, very constrained in terms of how much data you could kind of feed an LLM. So if you're talking about like 512 tokens, you know, you're talking about like, you know, 40 or 400, 500 words, or maybe it's the reverse of that, but like something like relatively limited. Now you can basically go, you know, I think a lot of the models are like, hey, send it all of Shakespeare and go do something with it. Now, is that a good or bad thing? Now, obviously, RAG, again, I won't go spend too much in it. Like RAG is like, how do I go split my, you know, my content, stick it in a vector database and use it? It was one way of basically getting around like a bunch of data, and how do I give my large language model specifically the data that it needs, as opposed to my whole corpus. How do I go focus on, hey, what are the highest quality, you know, content I have? And I think it was partially motivated, you know, it really did take off. I mean, I think it was invented in like 2021, 2022. It really took off with like a lot of those more limited LLMs at the beginning. But now, like, all right, now you have a ton of room. But there's kind of some really weird behaviors in terms of how large language models treat kind of their context length. So one of the initial, like if people were playing around with large language models in like 2023, like ChatGPT 3.5, you know, Turbo was, you know, that was state of the art, you know, could deal with like, you know, 4,000 tokens. It had this really interesting behavior where, you know, depending on the content, so you go fed in, you know, in this case, you fed in like 20 different documents. It did a better and worse job depending on where it was, which obviously is not a good thing. So if it was like, say, like the first document, it did a very, very good job from a retrieval standpoint. Towards the middle, it was basically like average. So it's like basically the data didn't even exist. And then towards the end. Now, you know, maybe I like kind of comparing it to people. Like if you're listening to a conversation, you hear the beginning and the end, and like this whole middle section of my conversation will be just like droning. But you know, this is kind of a behavior that like these large language models, you needed to think about this, right? So if you're throwing a bunch of content at this thing, and it's basically just ignoring all the middle section, that's kind of a problem. So I think what people kind of did was like, all right, as these models got bigger, so this is an example of like a needle in the same thing. So needle in the haystack. How do I go find in a large corpus or in my context length specific content? So in this, the x-axis is the context length. So like, you know, starting like really small, getting up to 128K. And then basically this is kind of the document length. So like where it is percentage wise. And you kind of see this interesting behavior where it does pretty well. So like ChatGPT 4, that prior one was 3.5. So it was pretty rough, right? Like if it wasn't the beginning of the beginning or the end, it was not really necessarily going to use it. Whereas ChatGPT 4 did a pretty good job up until you can kind of see like around 70, you know, 73, 82,000 tokens. It started getting some weird stuff. And also similar to the last one, like there's like kind of a section of it that didn't do very well. Now, another one around the same time. So this is, again, both of these were from like the end of 2023, like Claude, pretty bad, right? So they pushed really, really hard marketing themselves. Hey, like you can have this really large context length. The reality is like, it did not do a very good job with all the information you fed, right? So, you know, again, as you're building models and you're feeding in a bunch of data, that's a problem, right? Because you're thinking, hey, like I can send it a book. It's not really processing it all the same. Like it really depends on the position, which is kind of really weird, right? That to me is, it's more of a challenge because like it's unreliable. So you want to build reliable, repeatable systems. This is where it works. And again, things have gotten a lot better. So DeepSeek, V3, if you're familiar, so like V3 is the base model that was used to train R1, which is the one that like tanked NVIDIA's stock price 2 weeks ago. Pretty solid, right? So now you can see, so again, like you can see the progression. I guess part of what I'm trying to show is like there's been progressions over the last, like we have these weird challenges in these large language models, and over time they improve. But you need to understand that if you were building a model or if you were building a system in summer of 2023, summer of 2024, now you have more capabilities. Whereas last year, or I would have been really scared to use Claude for anything, right? Now and again, their model's gotten a lot better, so I'm not shooting at Anthropic, but like you need to understand this if you're trying to use your context length to really feed a lot more data into it. Now, I haven't really talked about multimodal. I think this is the only one that I'll have in there, but it's kind of, there's a paper that was middle of last year that really looked at multimodal needle in a haystack. So what they did was, how do I go, so M is the number of images. So kind of going like, how do I feed one image, I feed 10 images, and then the other parameter N is basically the number of like the stitching size. So how many, blocks. So you can kind of imagine if there's a photo, you're really not necessarily like, hey, what is the photo about? I'm saying, hey, within this 8x8 grid, I'm really specifically looking for this pixel or this sub image. And you can see we have a huge way to go from like what these vision models are able to do. Like, so I think generally they're pretty effective. If you give them one image and it's basically kind of binary N. So if there's 4 different boxes, it did okay, but very quickly. I mean, 8 is not that much. So that is, 8x8, 64. They all just fail. So all this is, there's somewhat of an indication we have a lot of work to do, specifically around kind of, some of this multimodal stuff. I think we're beginning to figure out the tech side. The multimodal space is kind of a,
I have another question.
Yeah.
Again, I'm just
Yeah.
trying to generalize in my
Yeah.
brain.
Yeah.
So are you saying there's almost like there's a competition between size of the context window and the quality of attention? So maybe initially
It's even weirder. So,
okay.
So,
But you understood what I'm saying.
yeah. So we've been talking generally, I'm looking for one needle, right? So I feed a bunch of information and you can say, now it's doing really good with one needle.
Yes.
What if I need 3 facts? What if I need 10 facts? Now, and this is like LangChain did this. Again, like this is, fraction of correct answers, right? So if you're asking for 10 facts, you're getting to like 50%. That's like flipping a coin. So number one is like, if you're really, so I'll just say, it's like, if you're looking for needles, look for as few as you need. If you add more, these models, you might potentially need to think about a different mechanism of doing that. Because generally they're not very effective. And it's kind of like very similar, you get the same diagram, right? Really, really good with like kind of small context length. As you increase the size of your context length, it gets really, and it's, maybe they just graph it. So it's always like the upper right is like dangerous, but I mean, this is kind of a pattern there.
Does it get better if you split it up into 10 runs on context length of 1?
Correct. Yeah. So that's why, I mean, I'm a little bit biased because like when I started doing RAG, I was like using 3.5 and I could only have like 4.5. So I'm trying to make my context window as small as possible. So if you're doing RAG, doing like cascading retrieval, re-ranking, try to minimize that, because if you go dump all that documents, there's just some more unpredictability, which is what we're trying to avoid, right? Now again, I think it's great they claim that you can feed it a bunch of data, but clearly, depending on how you're using that data, it might not necessarily be doing a very good job.
So you see an emergence of shims that can overlay that?
Well, I would say, I guess one of the reasons why I showed this one, it's going to get better, right? So DeepSeek, I mean, again, they've done some really phenomenal things from like an attention mechanism, like this is like leading edge, right? Right now, if you're using an LLM for multiple things, I onesie twosie it until these models get better, right? Now, somewhat we'll get into reasoning. So I guess agentic thinking is one of them. That's one of the motivations why you're starting to get in there. But But I'll continue on this journey of all these weird like LLM behaviors that we need to be thinking about because they don't, so the next one is, I'll kind of go through this a little bit more quickly, like, so premise order, right? So this is an example of like a prompt, like a prompt. And depending on like where you put this fact, like it can actually get it wrong, right? So it's like, again, this is not like a human, right? So you give like, hey, here's my 5 axioms that you need to follow, and I shuffle the order of the axioms. It changes behavior, right? So this study was an interesting one. So they did, they basically kind of like reordered stuff. So Ford, so I mean, these are admittedly a little bit older models, but it kind of shows like the blue line is like really forward. Like the red line is like they basically just reverse the order of the facts, and then they're shuffled as that. And we can see it now. Now it's a little dangerous because I will flag like the index, the y-axis is like a different. So this is like 1, it's like 100% to 80% is like from 0 to 1. But like those models, like they fall off a cliff. Like if I reverse the order of my facts, and that to me is like indicative, like, all right, there's something not very robust in the way that the large language models. If it really is that dependent on how precise the data is being fed, like something else is going on. Similarly, they added in distractors, right? So same kind of thing. They basically added information that was not useful. And you kind of see that curve like going down faster. So all to say is like, again, it's coming back to when you're thinking about your context length, your context window, really think about exactly what you need, as opposed to just, praying, hey, throw a bunch of data at it. It's magic, you're going to figure it out. Because there's again, it could, but it also might be unpredictable. And that's really hard if you're trying to build a system that's reliable. So all to say is like, I kind of like.
It gets overwhelmed.
Yeah, or like, you throw a bunch of data, like it's maybe back to attention, back to temperature. Like it's trying to predict what's next. But if you have a bunch of noise, it's like, hey, you have this big window, but I want to really focus on just that, we'll just send that versus I just gave it all this information that it doesn't know what to do with, right? And I just like this diagram, like, I mean, a little bit more reasoning, but it's like, we need to be careful. Like a lot of prompt engineering is basically like, hey, I know exactly the answer. Looks like it's doing these really great things, but like, I'm really just hyper tuning that like prompt, right? So, just something to kind of keep in mind. So, all right, I'm going a little slower than I thought, but last section. Is this okay? People are still awake? We're in the middle section, like this is, I don't know how much people will remember, but that's okay. So the last one, I really wanted to get into like reasoning and like agentic AI, and they're kind of very combined together. And I think when you start thinking about reasoning, we need to define like what is reasoning. Now, I don't think this is like a perfect set of definitions, but I think it's like very helpful for this kind of like not necessarily a toy example, but a really, really good small enough example that I'll kind of go through in the next few slides. It really kind of shows some of the strengths and weaknesses of what LLM is able to do. So I think memorization, really just being able to identify patterns. So, but then again, as hopefully you have an appreciation, like that accuracy. So if it's memorizing, if it's the training data has a bunch of examples, it's going to do a lot better, right? So that's definition of memorization. Probabilistic reasoning. So the model is choosing output that is more probable. So like, again, if you feed it a bunch of examples, it's going to be more accurate for those. But again, like it's somewhat hinting at if you have like things that are out of, like kind of more, random events or kind of more outliers, it's not necessarily going to do as well. Symbolic reasoning, I think that's kind of like the gold standard. So if it could actually interpret like what the rules it should be behaving, it should get 100%, right? If it understands the rules. And then the fourth one is a little bit like, it might have an approximation to symbolic reasoning, so it might not necessarily get it or not. But like, that's an example where, like if there's more steps, you're going to have more noise, which obviously becomes a concern, like when you're starting to build agents, because if you have a noise system and your error bound is just getting bigger, right? So what was interesting, these next few papers, it's interesting. I don't know why people got really interested in using a Caesar cipher. So I think probably everyone's played around with one of those, like when you're a kid, like in like the Cracker Jacks box or whatever. Like it's basically a dial, and like it's kind of like a rot. So you see rot n. So it's basically if it's rot 0, then it's like okay, the 26 letters, and then rot 1 is like move it by 1, that kind of thing. So this is kind of a really nice example of kind of a problem, right? It's from a person. You give this to most kids. like most elementary schools, they'll figure this out, right? So they understand, they'll going back to this reasoning, they probably understand the symbolic reasoning. Okay, I understand what happens. You can kind of test with, okay, how well does an LLM do, right? Are they actually reasoning? Could they figure out what this thing is doing? And this one of these papers, so Embers of auto regression, but I'll go into this. This one specifically just try to identify, so the task probability. So like, how likely is it? So on the right-hand side, it did ROT2, so it's just kind of shifting it to 2, or ROT13. And what you see is a very, very strong correlation with, like, so the note there is in internet, like ROT13, so basically just shifting it like around half, like it's 60 times more likely in the internet than ROT2. And it's kind of somewhat reflective of the training data, so that your training data actually allowed your models to do a lot better with ROT13 versus ROT2. That's more fundamental, like that's fundamentally because of the data that you use to train the model versus it's not really figuring out anything. This is, I think, a really good example of like memorization. So it's just trying to match those patterns that existed within your training set. The other example would be, example of like decoding like high probability outcome. So if there's like an output that's like more likely, that like makes sense, they do much better versus one that's like a medium probability or low. So again, that's somewhat talking to, if you're expecting an output that's much more of anomalous, it's going to struggle with that because it's really focusing on what is the most likely scenarios. And again, that's somewhat coming back to our temperature dial. So if I have a low temperature, I'm really trying to focus on what is the most likely behavior that I saw in my training set. And I think very similarly on your input side, if you're asking a question that's more likely, it's going to do a better job than something that's like less probabilistic. So I think kind of some of the key takeaways is nuance of LLMs. They perform worse on rare tasks than on common ones. I mean, that's kind of to be expected. So again, if you're trying to use these things for rare tasks, you need to be careful because they're very much focused on what is the most likely scenario. And secondarily, they perform worse on examples of low probability answers. So if you are trying to use it for very, very precise like things, I think you were asking about like for a location of a restaurant in Plymouth, it's not going to do very well, right? Versus a high probability. So that's kind of like you're kind of beginning to feel like, all right, this, the way the LLMs are trained, there's biases in the way that they solve problems. I think is a very important thing to keep in mind. Yeah.
So how do you think, do you feel that gap is getting filled up by commercial RAG data sets?
I would say no. So this is a very different, so the second section was really around RAG for data. Now we're really focusing on like, what can a large language model do? So this is independent of, I mean, obviously you can improve, well, why don't you pause that? So we now hopefully have some appreciation. These large language models are really just, it depends on how you train, right? You can kind of tweak them. And they have some odd behaviors. They're not really able to use like multiple needles. If you reverse the order, they get confused. In this case, they really just are biased towards things that are like the most common. And like we start thinking about like, how do we solve for those types of problems? And I don't want to get, I mean, I'm really not talking too much about prompt tuning, but most people have probably seen, like chain of thought. Like the only reason I want to show this is there's a bunch of other permutations. So there's like, multiple chain of thoughts. You can run them and like prune them, tree of thoughts, people might have heard of, like graph of thoughts. So the reality is a lot of people are now what people are beginning to pick at is, how do I kind of try to emulate the way that humans kind of talk through reasoning of problems versus just this one-shot behavior? So a lot of what we've been talking about is like, I give it a question, it's giving an answer, and there's really not a ton of help in the middle. Whereas like in the chain of thought, maybe we can help our agent kind of think through the problem and see if they can actually do better. And I think this is really, and again, I'm mainly showing this, so there's a bunch of opportunities here, but like chain of thought, we kind of followed that. Let's look at kind of like chain of thought. And I think what's interesting is, so like, again, going back to our nice kind of, Caesar site for the ROT, standard prompting, most of your models, like, so this is, again, another model, Claude 3, could not figure it out, right? It's not able to figure out like that ROT, like that shifting. However, it's interesting, if we add a chain of thought into our prompting, we're actually getting some pretty decent behavior. Now, it's not 100%, right? So we don't think it's figuring out the symbolic reasoning aspect of things. However, with the addition of chain of thought, it does relatively well. So it feels like if we add a chain of thought, if we actually started to chain together what these large language models do, maybe we can actually get something that's going to be a little bit better than kind of like what we saw before. And that kind of somewhat gets us to DeepSeek 3R1. And I think and one of the reasons why I want to show that, like on a base model, training, the alignment training, and then like kind of doing something with it. They basically took a really solid base model. So their DeepSeek V3. So that was a kind of a state-of-the-art model that was released. Interestingly, they took, as opposed to reinforcement learning human feedbacks, as opposed to that, they took like reasoning traces. So they took examples of like, how do you think through the solution of problems? So as opposed to feeding it, hey, is this like a human or not? They're feeding it reasoning data. They did a bunch of reinforcement learning. And this is out pops like the latest and greatest like reasoning models we have. Now, I think it's very highly rumored that like OpenAI, like their O3, their O1, they're doing something very similar. So as opposed to alignment training with reinforcement learning, human feedback data, they're training with chains of thought. And what we're ending up with is these reasoning models that are much more effective at kind of basically chaining together. And ideally, maybe doing a much better job, like kind of problem solving on these surfaces. Whereas like out of the box, most of these LLMs are not very effective. And so I think what you have now is, this is an example from like OpenAI, I forget if it was like their O1 or, I guess it doesn't really matter, but like now it's like turn-based, right? So we're saying, hey, turn 1, you have an input, there's some reasoning data that you want to capture, and then there's an output, turn 2. So there's really kind of getting into this chain of thought, and we're beginning to see, and this is why these reasoning models are able to solve kind of some of these closed domain problems a lot more effective than your LLMs of even like 3 or 6 months ago out of the box. Yeah.
So are you saying, when we started machine learning, we said, instead of really codifying logic or writing the rules in the programs, let's the outcome, let the system predict, what the next outcome would be. Now, with what you just explained right there, we're trying to go slightly back. We're feeding back the logic.
What I would say is like, so the first models, we were basically training it to be really good chat engines. So ChatGPT trained it to like behave like a person. Now we're trying to behave it like, all right, how do I go? Here's where I start. Here's the end. How do I solve that? How do I solve that solution? And here's some problems solving techniques.
Samples of logic.
Correct. Correct.
Yeah.
And then again, like chaining it together, right? Because again, that's how a lot of, this is how we think through problems, right? Like how do you chain it together versus like one shot, right?
When machine learning started, we just said we don't need that at all anymore.
Well, I'd be cautious. I'm not sure, like, I wouldn't say machine learning, but like the way that your large language models were initially trained.
That's right.
A lot of this talks like, you need to understand why people are training models. OpenAI built their initial models for chat.
Yes.
Well, maybe not necessarily for chat, but it was optimized for a chat scenario. Now we're beginning to see a lot more focus. They're optimizing. And there's different training techniques they're doing. Now, again, these are the same training techniques that are already being used. That's why I think that's one of the most novel things about DeepSeek. They didn't really think of a new way of training. They basically thought of a new formula. So how do I use the same ingredients? Use reinforcement learning. Reinforcement learning is pretty standard.
So
right?
now we need new specialists who can design that high quality reasoning data.
Correct. So that's why like synthetic data is like going like crazy. So everyone's generating, and I think it's rumored that like, OpenAI has like 30 trillion, whatever, like tokens, and then they're beginning to optimize. So this is like the new, like arms race around a lot of these large language model builders. They're trying to build, all right, how do I get a bill? And this is also why like, so OpenAI is saying, hey, DeepSeek used OpenAI to basically create some traces, because this is becoming like the new battleground for how do I get the best data set to be able to kind of tune my models to get kind of a better reasoning model.
Who did they find the data set for the yellow, the high quality reasoning data?
Well, yeah. So I mean, OpenAI is saying they basically.
They created.
Well, no, OpenAI is saying like DeepSeek just basically queried O1 mini and basically, well, they probably did their own, but they also were hitting some of the other models to basically create those traces. So, but that's.
How does it relate to like a multi-layer percent fund where you kind of want this assembly line of neurons that each have a specialized function and takes the output from the previous and kind of carries it?
Yeah, that's what I mean. Well, okay, so we're kind of, maybe a different talk. We can talk about like mixture of experts. Like, there's another, we're kind of getting this around, like you have maybe potentially multiple agents like chaining together. You don't necessarily need to have like the same engine. I think the main point is what's happened over the last 3 to 6 months is they focused on a different training set. And that fundamentally, X number of parameters, same training, roughly the same training techniques, you're getting a very different model behavior. So these models behave very differently than the chat models that were optimized before. And that's, again, what's interesting is like, all right, how do we go? Like, there's a lot more room for optimization within your large language models than, what we thought, right? I think everyone thought like OpenAI was doing something magical with like the reasoning models, but now DeepSeek, they said, like, meat and potatoes, right? We just chose different training set, reinforcement learning. We didn't do human feedback, right? Because we don't really necessarily care about like what a human thinks. And then we're getting much better reasoning engines. And it's, you've seen, I didn't include all the like the charts, like, hey, how much better the benchmarks are. So I'm getting there. All right. So all to say is like, then we get to agents, right? So hopefully now you have appreciation of reasoning. So I think I like that Caesar example just because it really shows that like most of these large language models, I personally don't think are reasoning, right? They're really pattern matching what's already fed to them. However, we're beginning to get to like, how do we stitch them together? How do we use them in some sequence in a more effective way? And I think that's why everyone's been interested in agents. Now, I think most of the people don't list, the first one. So like memory, knowledge, profiling. I think it's very, very critical. And this is also why I wanted to talk about RAG and the input, like the data that these models work are kind of like fundamental. So that's like kind of foundational. I think most people are familiar with like planning. So these models are able to like, hey, X number of steps, tool use, kind of go, basically call out to the web, to a SQL database, to a bunch of things. I think reflection is a really critical thing. So especially if you're trying to avoid hallucinations, how do I have my model actually check its own work as part of that process? And then, I think we've somewhat talked about like kind of multi-agent collaboration. So these are, I would say like kind of the 5 building blocks that are out there. And I think people are really trying to figure out how do we go use these together to kind of really build like the next generation of models. And again, I think this is a little bit of an older example, but Andrew Ng, which I'm guessing most people are know, he had this chart on one of his presentations where he showed like, GPT 3.5, GPT 4, and he kind of showed on the right-hand side, if you added in some of these agent ways of like, if you add in like kind of planning, if you add in reflection, you're actually able to kind of leverage your 3.5 could behave very, very similar, or at least like from a benchmark standpoint than 4. And I think I like this because now, like right now we're bootstrapping up to the next model. So now we have our reasoning models. It's going to allow us to kind of get even further. And I think maybe going a little bit back to like the DeepSeek and where they got the data from, a lot of people are thinking like, OpenAI is using GPT-5 to generate training data for their new models. So I think so what's happening is a lot of the best models are being used to bootstrap to try to get better training data to kind of uplift all the models. So wrapping up, I think I'm not that off from an hour, but all to say is, so this was a chart from OpenAI, and I really liked these 2 dimensions, and I think hopefully these very much align with kind of what we've kind of talked around. Number 1 is really the data, so the context optimization. We really want to be thinking about as we're formulating our large language model or whatever AI solution we're making, we really need to kind of think about what does the model need to know to be able to solve that problem. And the other dimension, which I think is very, very critical, and again, this is really why I wanted to spend so much time on the context length, the RAG, maybe it got boring, but I think it's really important to understand the data is really critical. But then that second dimension is really how the model needs to act. I think it was a little bit, before this like reasoning stuff, it's kind of generic. I think like fine tuning, I think it was just really hard for most people. It didn't really make necessarily a ton of sense. Now we have these reasoning models. So now we have like this is kind of like this new vector kind of going up. So all to say is like, hopefully, like this gives you some appreciation. Maybe it was a little bit too much. Maybe it was a little bit too little, but really there's just a lot of knobs, right? I think there's a data dimension, there's a capability dimension. And I think as users, as builders of these solutions, I think it's very valuable to be keeping them in mind because I think it's important for us if we're trying to build systems that actually are, successful in whatever your goal is. That's really critical. So, wanted to leave with this. I think we actually were having a conversation about a few people before, but like I don't know. Like I don't know. It's more just I'll leave it out there. But yeah, like Anthropic, like don't use AI, in your applications. Like we're just in this weird spot where, like, in my opinion, is like, I would strongly recommend everyone here like use these models, experiment with them, each one of them has like a different character, a different personality. And I think that's a good thing. And I think people are going to be optimizing and improving these. Like, I don't think it's going to be like a one size fit all. I don't think it's, or one, it's not going to be like Google, right? There's not going to be one search player that owns the entire market. I think it's going to be much more fragmented. And I think part of it is really as users, as developers, as technologists, I think it's really fun to play around with these and figure out like which ones are good, which ones are bad. So, and use AI for your application or job applications. So, all right. Well, thank you very much. Hope this is helpful. And
That was awesome. Thank you, everyone. Did I see a hand up? One last question here. We gotta get going.
Yeah, I have a question on context conflicting when things get too complex.
Yeah.
Is there any like rule of thumb for that you notice?
I mean, so what, yeah, I took out an example. So there's an example, we built a chatbot, like a RAG solution for one of our clients. And we've had this really interesting behavior where like people that interact with it with a bunch, they start having hallucinations after a certain point. So I think, kind of back to that context link, what we're looking at doing is we're trying to figure out some threshold where we start summarizing the history as opposed to just feeding it. I think it's a good, like, this is a good, back to this one. Like, so like at some point you need to truncate. I think we're looking at basically, you need to truncate a lot sooner than the 128K token window. So I think but again, like in many cases, you don't need the whole history. You can just do a summarization of that. So I think that's one example where we would recommend don't try to go hit the limit of your token, your context line.
So you think tokens are one of the biggest factors that causes this?
Yeah, 100%. I mean, we have not changed the model. We don't change the prompt. The only thing that's changing is the history. As history gets bigger, we have more variability in the responses. So
One of the things I was thinking of is there's a book called The Alignment Problem. If anyone's ever read that, that's a really, really good book. I would highly recommend it. It's by Brian Christian. And it talks about bias in data and about just the ongoing effort that we're trying to basically make these large language models kind of align with human values, and still a lot of problems in it. So for sure, but yeah, it's a really good book. In fact, I think it came out in 2020. It's a little bit of an old read, but it's totally still applies today.
2020 is an old read.
Yeah. We were just. Yeah. Cool. All right. Well, thank you, everyone.
Thank you very much.